The Pelješac Bridge's construction utilized a record-breaking 130.8-meter-long steel-driven pile, the longest and largest of its kind worldwide. Over 31,000 steel tubular piles, essential for the Pelješac Bridge's stability, were shipped from China in 6 batches, ensuring timely delivery despite global shipping constraints. These piles, primarily over 110 meters in length, around 70% of them, were engineered to withstand the bridge's immense load requirements and challenging marine environment, providing a deep, secure foundation for the entire structure. To construct in 27-meter deep waters, 12 specialized engineering ships from China arrived via a semi-submersible barge, enabling complex marine operations. The steel TVE composited cofferdam was used to create a dry, stable work environment underwater, facilitating precise pile cap construction. 10 pile caps were constructed directly in seawater to anchor the bridge's massive steel piles. Built with high-strength materials, these caps stabilize the foundation by securely distributing load forces across underwater structures. The bridge's piers feature hollow sections and enhanced wall thickness, providing a balance between strength and material efficiency. This hollow design reduces weight while maintaining stability, and the reinforced wall thickness ensures resilience against environmental stresses like water currents and wind. The superstructure includes 34,700 tons of steel box girders, providing strength and stability, essential for supporting heavy loads and resisting wind forces. A 1,000-ton capacity floating crane was used to lift massive bridge segments, enabling precise placement of heavy components efficiently and safely. The bridge construction utilized 56-meter-long large segments, reducing the need for on-site welding and accelerating assembly. These extensive segments were lifted by a 1,000-ton capacity crane, allowing seamless integration into the structure while ensuring stability and alignment. The construction employed 250-ton capacity derrick cranes to lift and position 12-meter-long standard bridge segments with precision. These smaller segments, installed sequentially, allowed for balanced cantilever construction, enhancing structural alignment and facilitating efficient assembly of the bridge's spans. Wind resistance cables and stay cables were strategically installed to enhance the bridge's stability and structural integrity. These cables counteract lateral forces and provide support to the main spans, ensuring safety and performance under varying environmental conditions, especially strong winds. Before any physical work could commence on dismantling the old bridge, engineers and workers undertook a critical preparatory phase. Given the bridge's central role in supporting rail services, extensive protection measures were established to ensure the stability of the structure and safety for both workers and nearby infrastructure. These measures included laying reinforced protection materials around the bridge, helping to distribute the load and minimize potential impact on the existing tracks and nearby structures during removal. This initial phase not only safeguarded the bridge, but also provided a stable base for the equipment and machinery required for the upcoming dismantling. The level of preparation and attention to safety here underscores the complexity involved in working on historic rail infrastructure in a high-traffic location. The removal of the last piece of track on the Rickmansworth Met Rail Bridge was a crucial step in the bridge replacement project, marking the point where dismantling could truly begin. This phase was carried out with careful precision due to the bridge's age and structural sensitivity, as well as its importance within the network. Removing the last segment of track required exact timing and skilled handling to ensure that the bridge's stability wasn't compromised, particularly since this structure supported both London Underground and Chiltern Railway services on the Metropolitan line. Firstly, engineers inspected the track thoroughly to assess any areas of potential weakness or stress that might shift during removal. Once cleared, the final segment was separated from the adjacent tracks, and fastenings were slowly unbolted, with teams positioned at both ends to stabilize the track. Using specialized lifting equipment, workers then carefully hoisted this final piece away, mindful of balancing the weight evenly to avoid any unintended shifts in the bridge structure. As they removed it, the team constantly monitored the bridge for any signs of stress or structural change. Engineers had placed supports around the bridge foundation and the remaining track sections to prevent any part of the structure from moving unexpectedly. This careful removal of the last piece of track allowed workers to access and evaluate the condition of the bridge deck itself, ensuring that it was safe to proceed with the tentative lift. Additionally, clearing this segment set the stage for installing the new bridge, which required precise alignment with the remaining rail infrastructure. The first tentative lift of the old Rickmansworth Met Rail Bridge was a pivotal and delicate phase of the bridge replacement project, requiring extensive preparation, precision, and coordination. This initial lift was a cautious trial intended to separate the bridge from its supports and evaluate how it responded under the load of the crane. Given the bridge's considerable age and weight, as well as its long-standing integration with the surrounding infrastructure, engineers approached this lift with meticulous planning and an emphasis on safety. Before attempting the lift, engineers had already carried out substantial preparatory work. This included reinforcing the surrounding area and clearing the bridge of any remaining track sections, which reduced the overall weight and relieved stress on the bridge deck. Engineers conducted multiple structural assessments, studying the condition of the bridge and identifying potential weak points that might create issues during lifting. This involved checking for rust, degradation in the materials, and signs of stress fractures, all of which could compromise the integrity of the bridge as it was hoisted from its position. Additionally, teams had set up load distribution materials and safety supports around the site to prevent any shifting that could destabilize the bridge during the lift. The crane chosen for this task was a specialized high-capacity crane equipped to handle the significant weight of the bridge. This type of crane has precision controls that allow for minute adjustments, essential for moving such a heavy structure smoothly. Positioning the crane was a logistical challenge due to the limited space around the bridge site and the need to avoid obstructing nearby tracks or affecting surrounding infrastructure. Careful calculations determined the optimal placement of the crane, ensuring it could lift the bridge while maintaining stability. The crane was strategically anchored to prevent any sway or movement that could compromise the lift, and operators ran multiple test lifts with lighter materials to verify its functionality and alignment. Once the crane was in position and all equipment had been tested, engineers initiated the first tentative lift. This lift was slow and highly controlled, intended to lift the bridge only a few inches off its supports to test its response to the upward force. By starting with such a slight lift, engineers could observe any immediate reactions, such as creaking, cracking, or shifts in weight distribution, which might indicate structural weaknesses that hadn't been evident before. Throughout the process, a team of structural engineers and crane operators maintained constant communication, monitoring pressure points, and checking for signs of strain. To mitigate risks, engineers paused the lift at multiple intervals, allowing for inspections at each step. These pauses were critical, as even slight changes in the bridge's alignment could signal potential problems. During these pauses, engineers assessed load-bearing points and verified that the bridge's weight was distributed evenly across the crane's lifting apparatus. This stop-and-check approach allowed the team to address any issues before they became critical, ensuring the bridge's integrity as it was gradually lifted. A comprehensive monitoring system was in place throughout the lift. Engineers used sensors on the crane and on the bridge itself to track weight distribution and detect shifts in real time. Additionally, visual monitoring by inspectors stationed around the site provided immediate feedback on the lift's progress. This multi-tiered monitoring approach was essential for such a delicate operation, as even small shifts could create hazards, not only for the workers but also for the stability of the surrounding infrastructure. Safety precautions were of paramount importance. Workers were instructed to stay at a safe distance from the bridge during lifting, with only essential personnel stationed nearby to manage the operation. Emergency protocols were in place to handle any unexpected issues, a sudden structural failure or mechanical issue with the crane. This included having a secondary support system ready in case the bridge needed to be quickly stabilized. Engineers also conducted safety briefings with all personnel involved, ensuring everyone was aware of their roles and responsibilities during the lift. The first tentative lift concluded successfully once the bridge was raised several inches and held in position without signs of distress. This successful lift validated the stability of both the bridge structure and the crane setup, allowing engineers to proceed with the full lift and eventual removal. This initial step provided valuable insights into the bridge's behavior under load, confirming that the structure could be safely moved across the A412 during the next phase of the project. The Rickmansworth Met Rail Bridge night maneuvers was an essential part of the 2016 bridge replacement project, undertaken to safely remove the old bridge and transport it across the A412 road. This operation took place during the early hours of the 26th of March 2016 under the cover of night to avoid disrupting daily rail services and traffic on this busy road. The nighttime setting was ideal for minimizing public inconvenience, allowing the team to carry out this delicate and complex maneuver with maximum control and minimal risk. The maneuver was months in the planning, with meticulous coordination between engineers, transport specialists, crane operators, and traffic management teams. In preparation, the team conducted multiple site assessments and route mapping exercises, accounting for every detail from the bridge's size and weight to the exact dimensions of the station forecourt and the road crossing. They prepared for potential obstacles, such as streetlight signs and the incline across the A412, to ensure the bridge could be moved smoothly. The operation was timed precisely, with the team given a limited window to complete the movement before the first trains resumed in the morning. Every aspect of the move was planned down to the minute, with contingencies in place to address potential issues that might arise. To execute the maneuver, the project relied on heavy-duty equipment specifically designed for moving large structures. The bridge was first lifted by a high-capacity crane that could handle its weight, which was no small feat given the aging bridge's considerable mass. Lifting the bridge required extreme precision, as any imbalance could have caused structural strain or compromised the bridge's stability. Once the bridge was elevated just enough to be mobile, it was carefully lowered onto a set of self-propelled modular transporters, SPMTs. These multi-wheeled vehicles are engineered to transport massive loads, allowing for precision control and real-time adjustments to keep the structure balanced and secure. The SPMT's modular design meant they could adjust their height and distribute weight evenly across the bridge's entire length, minimizing stress on the aging structure. The initial part of the maneuver required moving the bridge out of the narrow station forecourt, a challenging feat given the limited space. SPMT operators, guided by ground crew, moved at an extremely slow pace, ensuring every turn and alignment matched the pre-planned path exactly. Due to the confined space, the transport vehicles had to make slight adjustments as they maneuvered backward, with operators coordinating closely to avoid any collisions with nearby infrastructure. Once clear of the forecourt, the SPMTs began the bridge's journey across the A412, a carefully planned nighttime crossing. The A412 had been closed to traffic for the maneuver, with detours in place to keep the area secure. Floodlights illuminated the route, and barriers surrounded the work zone to prevent unauthorized access. As the bridge moved forward, the operators kept a steady, cautious pace, closely monitored by engineers and ground personnel who communicated real-time feedback to ensure the bridge remained level and stable. The movement of the old Rickmansworth Met Rail Bridge out of the station forecourt and across the A412 was a carefully orchestrated maneuver that required precision and specialized equipment. This part of the project took place late at night to minimize disruption, allowing the bridge to be removed without affecting the usual flow of traffic or rail services. Engineers had planned the process down to the smallest detail, knowing that moving such a large, historic structure through a narrow space presented unique challenges. The bridge was first lifted off its original supports using a high-capacity crane, just enough to allow a set of self-propelled modular transporters, SPMTs, to slide underneath. These SPMTs are heavy-duty transport vehicles with dozens of independently controlled wheels, ideal for carrying massive loads across short distances. With the bridge securely positioned on the SPMTs, the team began the slow and careful process of backing it out of the confined station forecourt. Navigating the bridge out of the forecourt was a meticulous process. The SPMTs moved at a glacial pace, with operators constantly adjusting the wheel angles to maneuver around any obstacles. Ground personnel walked alongside the transporters, guiding them to ensure precise positioning and alignment, as even minor shifts could cause complications. The transport vehicles backed the bridge out at a slight angle to clear the narrow space, carefully balancing the structure's weight. As the old bridge was moved to a secure holding area, preparations for the installation of the new bridge at Rickmansworth Met Rail Bridge site began in full force, with the goal of positioning the replacement structure by 2 a.m. the following morning. This stage of the project involved meticulous planning and coordination across various teams to ensure a smooth, safe, and timely installation. Working within a very tight overnight schedule, engineers and construction crews focused on ensuring that the new bridge would fit seamlessly into the existing infrastructure with minimal adjustments. In preparation for the new bridge, teams began by inspecting and finalizing the abutments, the supporting structures at each end of the bridge, which had been reinforced and refurbished to provide a stable foundation. Engineers conducted thorough checks of these abutments, examining them for stability, alignment, and load-bearing capacity, as these structures would ultimately support the weight of the new bridge. Laser levels and alignment tools were used to ensure the new bridge would sit perfectly on these supports without causing misalignment or structural stress. Since the installation was scheduled for the early hours of the morning, heavy lifting equipment, particularly the crane needed to position the bridge, was staged well in advance. The crane, capable of lifting the new bridge's considerable weight, was precisely positioned near the track. Engineers verified the crane's placement and balance repeatedly, testing its swing radius and lifting capacity to prevent any issues during the lift. This setup process also involved positioning counterweights to balance the crane, ensuring stability as it lifted and moved the new bridge into place. The new bridge, pre-assembled off-site, had been transported close to the installation area and was undergoing final alignment and inspection. Crews used hydraulic jacks to make minor adjustments to its height and angle, ensuring it matched the specifications of the track and abutments exactly. Temporary support structures were placed underneath the bridge to secure it during the final lift, allowing the crane to handle the structure without risking any misalignment. The Rickmansworth Met Rail Bridge replacement in 2016 was an intricate and meticulously coordinated operation, replacing the aged Mr. 88 bridge that served as a critical part of London's Metropolitan Line infrastructure. Located in Rickmansworth, Hertfordshire, this bridge replacement was essential to ensure the continued safety and reliability of the rail network, as the old structure had aged significantly. Over the Easter weekend of the 25th to the 27th of March 2016, the bridge removal and replacement were carried out in a series of precise, phased steps, including late-night operations and complex maneuvering across a busy road. The Rickmansworth station, located in Travel Card Zone 7, has a rich history, dating back to its establishment as a terminus of the Metropolitan Railways extension from Pinner in 1887. Over the decades, the station has played a pivotal role in connecting Rickmansworth to Chesham, Aylesbury, and central London. The original Mr. 88 bridge was an essential part of this network, facilitating movement of both London Underground and Chiltern Railway services. Over time, the bridge, like many other elements of the Victorian-era rail infrastructure, required upgrading to meet modern safety and operational standards. The 2016 replacement project was part of broader efforts to enhance the reliability and capacity of the Metropolitan Line. The station's importance continues as it serves as a key changeover point for train staff on the Metropolitan Line. The new bridge structure not only supports these ongoing operations, but also prepares the station for future improvements, including step-free access announced in 2018. The final countdown at Rickmansworth Met Rail Bridge marked the culmination of months of planning, preparation, and complex engineering maneuvers. This stage, which took place in the early hours of March 27, 2016, involved the final steps needed to position the newly constructed bridge into place, ready to support rail services once again. With the replacement bridge already transported to the site and initial setup complete, the team was focused on precision, timing, and coordination to ensure the installation was completed without a hitch. The countdown began with a series of final checks. Engineers and surveyors examined the bridge structure, using laser alignment tools to confirm that its measurements matched the abutments and existing track connections precisely. These checks were critical, as even minor misalignments could cause significant issues when the rail services resumed. The crane operators, who would execute the lift, coordinated closely with ground teams to review each stage of the installation, ensuring all equipment was calibrated and ready for the lift. Once everything was confirmed, the crane's lifting cables were secured to the bridge, and the final hoist began. This slow and deliberate lift was monitored closely by a team of structural engineers who checked for any unanticipated stress on the bridge or crane. The bridge was raised to a precise height, then maneuvered gently over the abutments. With spotters on both sides, the bridge was lowered millimeter by millimeter until it aligned perfectly with its supports. Kanwanerski Island. Section 1 involves significant construction efforts, with concrete works achieving a completion quantity of 39,582 cubic meters, representing 81.08% of the planned volume. The steel works are fully completed, totaling 13,214 tons, ensuring structural integrity and supporting the overall project framework for the development on the island. Kanwanerski Island. Section 2 has successfully completed all concrete works, achieving a total quantity of 27,647 cubic meters, which reflects a full completion rate of 100%. However, the steel works are only partially finished, with 10,974 tons completed, amounting to 53.96% of the projected total. This section's progress highlights the ongoing efforts to enhance the island's infrastructure. Kanwanerski Island. Section 3 has seen substantial progress, with concrete works completed at 51,525 cubic meters, representing 78.82% of the planned total. Additionally, steel works have reached 16,851 tons, which corresponds to 85.58% completion. This indicates a strong advancement in the structural framework and overall development of the section. Korabelny Fairway. Section 4 demonstrates significant advancement in construction, with concrete works completed at 34,273 cubic meters, which accounts for 91.13% of the overall target. This high completion rate reflects the project's focus on establishing a solid foundation and infrastructure in this section. However, steel works are still in progress, with only 2,572 tons completed, representing 45.26% of the planned quantity. The ongoing efforts in steel fabrication and installation are essential for reinforcing the structural integrity and ensuring the timely completion of the fairway, ultimately supporting the broader development objectives of the project in this area. Vasilyevsky Island. Section 5 has achieved notable progress, with concrete works reaching a completed quantity of 28,059 cubic meters, representing 77.09% of the planned target. In contrast, steel works are fully completed at 12,137 tons, ensuring structural support and integrity for the ongoing development, which is crucial for the project's success. Vasilyevsky Island. Section 6 has made substantial progress, with concrete works completed at an impressive 219,311 cubic meters, which accounts for 92.78% of the total planned volume. This high completion rate reflects the project's emphasis on robust foundational work. Additionally, steel works have been fully completed, totaling 256 tons, ensuring structural integrity and supporting the ongoing development in this section. The successful completion of both concrete and steel works positions this section for timely advancement and contributes significantly to the overall progress of the Vasilyevsky Island project. Vasilyevsky Island. Section 7 shows exceptional progress, with concrete works completed at 68,577 cubic meters, 96.92%. Steel works are fully finished at 8,326 tons, ensuring structural support for the project. Petrovsky Fairway. Section 8 reflects significant advancements in construction, with concrete works completed at 20,051 cubic meters, achieving a completion rate of 91.46%. This high percentage indicates a strong commitment to establishing a solid foundation for future developments in this area. Meanwhile, the steel works are progressing well, with 4,460 tons completed, representing 70.64% of the planned total. This ongoing fabrication and installation of steel components are crucial for reinforcing the structural integrity of the fairway. The project's overall progress in Section 8 underscores its importance in enhancing connectivity and supporting the broader infrastructural goals of the region. Krestovsky Island. Section 9 has completed steel works fully, totaling 17,346 tons, which ensures structural stability. Concrete works stand at 28,624 cubic meters, achieving 67.30% completion, reflecting ongoing efforts to establish a solid foundation for the project. Savashkina. Section 10 has achieved full completion for both concrete and steel works, with concrete totaling 20,248 cubic meters and steel reaching 7,942 tons. This remarkable achievement demonstrates a strong commitment to the project's structural integrity and overall progress. The successful completion of this section positions it as a key component in the broader development efforts in the area.